Um, Good afternoon, everyone. My name is Samuel Boateng from Group F. I'm studying data science. Today, I'll be presenting on a topic unveiling cache memory mapping techniques in computer architecture. This presentation will help us to understand how data is efficiently managed and accessed in a computer system using different cache memory mapping techniques. I'll dive and explain how these techniques impact performances and efficiency in modern computing. Okay, starting out with the first slide. Before that, we have to know the definition, or we have to know what a cache memory is. So over here, it is said that a cache memory is a small, high-speed memory designed to accelerate data access by storing frequently used instructions and data that is closer to the CPU. So what is basically saying is it helps speed up processing by reducing the time it takes to access data from the main memory, which is the CPU. Now, direct mapping. Direct mapping, we'll talk about the simplicity, the addressing, and the limitations. So simple addressing. Each main memory block maps to a unique cache line determined by a modulo operation. So what it's basically saying is direct mapping is simple and fast because each block maps to one specific cache line. That's what it's basically saying here. First lookup. Direct calculation of cache location leads to a quick access times. Direct mapping can also cause conflict when multiple blocks compete for the same line, which reduces the performance. So as I said, the frequent cache line collisions for competing blocks can degrade performances. Moving on to the next slide, talking of set associative mapping. The set associative mapping also allows a block to go into any line within a set, which reduces conflict and balance its performances. It is also flexible than the direct mapping, but then it's slightly more complex due to the need for searching within the sets. Moving on to the next slide, we'll be comparing the mapping techniques, the direct and the set associative analysis. From the table, we could see that direct mapping is simpler, is faster, and is cheaper, but has more conflicts or conflict misses. But for set associative mapping, it's more complex and is slightly slower, but it reduces conflict and improve or balance performances. Now, on this slide, there are two main cache write policies. And the policies are, we have the write through and we have the write back. The write through basically means the updates on both cache and memory at once, while the write back updates memory later. For replacement algorithms, we have the LRU, which means least recently used. This discards the least recently used items first. And we also have the FIFO, which also means first in, first out. It also replaces the block that has been in the cache the longest. And also, we also have the random, selects a block to place randomly. In all this, they decide which block to remove when the cache is full. Okay, yeah, optimizing catch performance. To optimize catch performance, it is important to find the right balance between its cost, its complexity, and their balanced performances. Therefore, a good catch design takes a holistic approach that combines all these mapping techniques with efficiency, rights policies, and their replacement algorithms. Looking ahead, future systems may also use smarter or adaptive algorithms and more advanced memory architectures to boost performance even further. Thank you. This is the end of my presentation.